For services, the requirements for equipment grounding conductors and parallel conduits differ from those for feeders. National Electrical Code Section 250.24 A4 permits the use of a single equipment grounding conductor and one of the service conduits, provided that it is sized according to the combined capacity of all the conductors in the parallel conduits. In your case, with 8 conduits containing 500 cm conductors, the required equipment grounding conductor would be 3/0 copper. You are not required to install a 3/0 grounding electrode conductor in each conduit. You can run a single 3/0 grounding electrode conductor in only one of the conduits. While not required, it is considered good practice to install an equipment grounding conductor in every conduit, especially for long runs or where there is a high risk of damage to the conduits. This provides redundancy and helps ensure the safety of the installation in case one of the conduits becomes damaged or disconnected. There are several advantages of using an equipment grounding conductor in every conduit. Firstly, redundancy. If one conduit is damaged, the other equipment grounding conductors will still provide a path for fault currents. Secondly, improved protection. Multiple equipment grounding conductors can reduce the risk of voltage stress on the equipment grounding conductor in case of high fault currents. Thirdly, ease of maintenance. It is easier to isolate and inspect individual equipment grounding conductors if they are located in separate conduits. The National Electrical Code, or NEC, provides specific guidelines for grounding and bonding to ensure electrical safety. Understanding these requirements is crucial for any electrical installation, particularly when dealing with parallel conduits and service entrances. Let's delve deeper into the NEC requirements. Section 250.24 A4 specifically addresses grounding electrode conductors for grounded systems. It states that where an alternating current system is grounded at any point, the grounding electrode conductor must be connected at that point. When multiple service disconnecting means are installed in accordance with Section 230.71, a common grounding electrode conductor shall be run to each service disconnecting means. The size of the grounding electrode conductor is determined by Section 250.66, which bases the size on the size of the service entrance conductors. However, an exception exists where more than one service disconnecting means is installed, as permitted in Section 230.2 or 230.40. The common grounding electrode conductor shall be sized for the combined service entrance conductors. Now, let's focus on the scenario with parallel conduits. As you mentioned, you have 8 conduits, each containing 500 cm conductors. According to the NEC, you are permitted to use a single equipment grounding conductor within one of these conduits, provided it is adequately sized to handle the potential fault current from all 8 conduits. To determine the appropriate size for the grounding electrode conductor, we must refer to Section 250.66. This section provides tables and guidelines for sizing grounding electrode conductors based on the size of the service entrance conductors. In your case, with 8 500 cm conductors in parallel, the combined ampacity is significant. Therefore, a 3/0 copper conductor might be required, as you suggested, but it is critical to consult the relevant tables in the NEC to confirm the exact sizing based on the specific installation parameters. Although the NEC permits using a single equipment grounding conductor in one conduit, the question arises, is it a good practice to install an equipment grounding conductor in every conduit? The answer is generally yes. There are several compelling reasons to consider this approach. Firstly, redundancy. In the event of damage to one of the conduits, such as physical breakage or corrosion, having an equipment grounding conductor in each conduit ensures that a reliable ground fault path remains available. This redundancy significantly enhances the overall safety of the electrical system. Secondly, improved fault current handling. When multiple equipment grounding conductors are installed in parallel, they share the fault current load. This reduces the impedance of the ground fault path, allowing for faster clearing of faults. A lower impedance path helps to ensure that overcurrent protective devices such as circuit breakers or fuses operate quickly and effectively, minimizing the potential for damage or injury. Thirdly, reduce voltage stress. During a ground fault, voltage can rise on the equipment grounding conductor. By having multiple parallel equipment grounding conductors, the voltage stress on each conductor is reduced. This can help prevent insulation breakdown and other issues that can compromise the integrity of the grounding system. Fourthly, enhance safety. Overall, installing an equipment grounding conductor in every conduit provides an extra layer of safety for personnel and equipment. It ensures that a reliable ground fault path is always available, reducing the risk of electrical shock and equipment damage. Considering these benefits, it's generally advisable to install an equipment grounding conductor in each conduit, even though it is not strictly required by the NEC in this specific scenario. Doing so enhances the safety, reliability, and long-term performance of the electrical system. Now let's address some common misconceptions and additional considerations regarding grounding electrode conductors in parallel conduits. Firstly, the size of the equipment grounding conductor. While we've established that you can use a single equipment grounding conductor, it's crucial to ensure that it is adequately sized to handle the combined fault current from all parallel conductors. Using an undersized equipment grounding conductor can be dangerous and can compromise the effectiveness of the grounding system. Secondly, material compatibility. When selecting materials for the equipment grounding conductor and associated connections, it's essential to ensure compatibility to prevent corrosion or other issues. For example, using copper conductors with aluminum enclosures can lead to galvanic corrosion over time, which can degrade the grounding connection. Thirdly, proper installation techniques. Proper installation techniques are essential for ensuring the effectiveness of the grounding system. This includes making sure that all connections are clean, tight, and properly torqued. It also includes protecting the equipment grounding conductor from physical damage or corrosion. Fourthly, documentation. It's essential to document the grounding system configuration, including the size and location of all equipment grounding conductors and connections. This documentation can be helpful for future maintenance and troubleshooting. Fifthly, periodic inspection. Periodic inspection of the grounding system is essential to ensure that it remains in good condition and continues to provide effective protection. This includes checking for loose connections, corrosion, and other signs of damage. Let's also consider some practical considerations when implementing grounding systems in real-world scenarios. Firstly, coordination with other systems. Grounding systems must be coordinated with other electrical systems, such as surge protection devices and sensitive electronic equipment. Improper coordination can lead to interference or damage to equipment. Secondly, grounding impedance. The impedance of the grounding system can affect its performance. Low impedance grounding systems are generally preferred because they allow for faster clearing of faults. Thirdly, environmental factors. Environmental factors, such as soil conditions and moisture levels, can affect the performance of the grounding system. In corrosive environments, it may be necessary to use special materials or techniques to protect the equipment grounding conductor. Fourthly, regulatory requirements. Grounding systems must comply with all applicable regulatory requirements, including the NEC and local codes. Fifthly, industry best practices. In addition to complying with regulatory requirements, it's also essential to follow industry best practices for grounding. This can help ensure that the grounding system is safe, reliable, and effective. In conclusion, while the NEC permits using a single equipment grounding conductor in one of the parallel conduits for service entrances, it's generally recommended to install an equipment grounding conductor in every conduit. This provides redundancy, improves fault current handling, reduces voltage stress, and enhances overall safety. It's essential to consult the NEC and other relevant standards to ensure that the grounding system is properly designed and installed. Remember to consider the size of the equipment grounding conductor, material compatibility, proper installation techniques, documentation, and periodic inspection. By following these guidelines, you can help ensure the safety, reliability, and long-term performance of the electrical system. Moreover, grounding is not a one-size-fits-all solution. Different types of equipment and different applications may require different grounding techniques. It's essential to understand the specific requirements of each situation and to select the appropriate grounding method. For example, sensitive electronic equipment may require isolated grounding to minimize noise and interference. In other cases, it may be necessary to use equipotential bonding to create a low-impedance ground plane. Always consult with a qualified electrical engineer or contractor to ensure that the grounding system is properly designed and installed. They can assess the specific needs of the installation and recommend the most appropriate grounding solution. Finally, remember that grounding is an ongoing process. The grounding system should be regularly inspected and maintained to ensure that it continues to provide effective protection. This includes checking for loose connections, corrosion, and other signs of damage. Any issue should be promptly addressed to prevent potential safety hazards. Grounding is a critical aspect of electrical safety and should never be overlooked. By following the guidelines outlined in the NEC and other relevant standards, you can help ensure that electrical systems are safe, reliable, and effective. Always prioritize safety and consult with qualified professionals to ensure that grounding systems are properly designed, installed, and maintained. Grounding plays a vital role in protecting people and equipment from electrical hazards. Understanding the principles of grounding and following best practices is essential for anyone working with electrical systems. Make sure to educate yourself on the latest grounding techniques and technologies to stay up to date with industry standards and best practices. Continuous learning and professional development are crucial for ensuring electrical safety and preventing accidents. Also, consider the importance of proper labeling and identification of grounding conductors. Clear and accurate labeling helps prevent confusion and ensures that grounding connections are properly maintained. Use appropriate labels and markings to identify grounding conductors and grounding points throughout the electrical system. Effective communication and documentation are essential for maintaining a safe and reliable electrical installation. Grounding is not just a technical issue. It's also a matter of responsibility and ethical conduct. As electrical professionals, it's our duty to ensure that electrical systems are safe and reliable. This includes properly designing, installing, and maintaining grounding systems to protect people and equipment from electrical hazards. Take pride in your work and always strive for excellence in electrical safety. The benefits of a properly designed and installed grounding system extend beyond safety. A well-grounded electrical system can also improve equipment performance, reduce downtime, and extend the lifespan of electrical components. By investing in quality grounding solutions, you can improve the overall efficiency and reliability of electrical systems. Always consider the long-term benefits of proper grounding and make informed decisions that prioritize safety and performance. Finally, remember that grounding is a shared responsibility. Everyone involved in the design, installation, and maintenance of electrical systems has a role to play in ensuring electrical safety. This includes electrical engineers, contractors, electricians, and facility managers. By working together and communicating effectively, we can create a culture of safety and prevent electrical accidents. Let's all commit to upholding the high standards of electrical safety and making sure that electrical systems are properly grounded to protect people and equipment from electrical hazards.